So in general, you can actually do this with any type of number. The idea is that if you give me some integer n, if you give me some base b, I always have the ability to run this process. What's nice about this is that it's actually connected to this process of doing this division over and over and over again. And we saw a little bit of that when we were looking at the number 37. The idea is that I first divided by this 25, and then I divided by a 5, and then I divide by a 1. As long as I keep on dividing, I'm going to constantly be recording those values that are going to go in there. And that process works no matter what your base ends up being. So if I looked at the number 313, if I wanted to think about what this thing looks like base 3, what I'm going to do is I'm going to constantly divide by 3. So I'm going to take that number 313, divide it by a 3. In this case, 3 goes into 313 104 times. What I'm going to be left with is a remainder of 1. What I'm going to do is I'm going to take that little quotient that was generated, so that number 104, and then I'm going to divide it by a 3. So in this case, 104 divided by 3 gives me 34 with a remainder of 2. And then I take that 34 and divide it by a 3, giving me a remainder of 1 and a quotient of 11. I take the 11 and divide it by 3. That quotient is a 3, the remainder is a 2. Take the 3 divided by 3, that's going to generate a quotient of 1 and a remainder of 0. And then finally that little quotient 1, 3 does not go into that thing anymore, but it does in fact leave a remainder of 1. What's nice about this is that this big chain of remainders that occurs ends up becoming these little weights that we utilize to actually bring back the number in question. What's going to happen is that that last remainder becomes the coefficient on the largest exponent. And you can see in this case that I'm going to have 6 little terms. One of those is going to come with an exponent of 0, then an exponent of 1, then 2, then 3, then 4, then 5. So that last term I'm going to represent as an A5. And it's going to be the value that comes with this 3 raised to the 5th power. And then I run this in reverse. The A4 is a 0, the A3 is a 2, the A2 is a 1, the A1 is a 2, and the A0 is then going to be a 1. And if I wanted to, I can take this collection of numbers and then reconvert this back to a base 10 version. And the way that I do that is simply by taking those numbers and then multiplying them by the correct power of 3. So in this case, the A5 is going to be multiplied by a 3 to the 5th. The A4 is then multiplied by a 3 to the 4th, and so on, all the way until I get A0 multiplied by a 3 to the 0. What you can see here is that that A5 was a 1, so it's 1 times 3 to the 5th, all the way down to the A0, which is a 1 times the 3 to the 0, which then gets recorded as 1 times 243, plus 2 times 27, plus 1 times 9, times 2 times 3, times 1 times 1, which is simply just 313. So that's technically what this little theorem statement says up above, is that if you give me a value n, I can actually represent this thing with these nice little weights and the corresponding exponent of my given b value. So in this case, these b's have to be integers and they have to be larger than 1. So that's going to be representing that little n viewed base b. And the way that I record it is I'm simply going to record those recorded coefficients. So in this case, the 313, that's the base 10 version of this thing. And then if I view this base 3, it's going to be the numbers 1, 0, 2, 1, 2, 1. And if you want to, you can actually start running this in reverse. The idea is that if I give you some of these numbers, I can always convert them back to their base 10 version. So if I give you the number 10011, this is the term that's going to correspond with 2 to the 0. That's the term that's going to correspond with 2 to the 1. That's the term that's going to correspond with 2 squared. This is going to be a 2 cubed, and then that's going to be a 2 to the 4th. So realize that there's always this indexing that's going to start at 0 and then go all the way up. So if there's 5 terms in this base 2 version, the largest exponent is going to be 2 to the 4th. So in this case, you can record this as 1 times 2 to the 4th, 0 times 2 cubed, plus 0 times 2 squared, plus 1 times 2 to the 1, plus a 1 times 2 to the 0. In this case, it gets recorded as a 19. Same exact thing happens if I look at these terms, let's say base 3. This is going to become the term that goes with 3 to the 0. This is with 3 to the 1. This is 3 squared. This is with 3 cubed, and that's supposed to be a 3. And then this is going to be with a 3 to the 4. And you can record this number 21021. Base 3 gets re-encapsulated as a base 10 number of 196. So it's a really slick process that's pretty easy to run. You can actually implement this thing on Sage pretty quickly. You do more or less the exact same thing that we saw in the Euclidean algorithm, is you're going to be constantly doing this division. But in this case, what's going to happen is that I'm going to take that quotient, and then that becomes the new number that I work with. So if you remember in the Euclidean algorithm, we were dividing by different things each time. The idea is that we started with a pair A and B, and then that B value became the next times A value, followed by the next remainder. What's happening here is that the division is always being done with the same base. So I'm going to be recording that in this fashion. So the idea is that 313 always divided by 3, and then this little term right here becomes my new starting place. So that's where the zigzagging action is going to occur. So in Sage, that's a pretty simple command. So I'm going to do this all the way until I get to that final stopping point. So once my quotient no longer can go in there anymore. And it's a little bit delicate in this case because you can see that it's kind of funky. That last step is that I get this remainder of 0, and I have this quotient value of 1, but I need to go one extra step. And it becomes important because that little value at the end becomes my largest coefficient, or my coefficient that goes with the largest power of 3 in this case. So I have to go all the way until I see a little 0 occur in my quotient. That becomes my breakpoint in this case. What I'm going to do is I'm going to, at each stage, take my quotient q, which is taking n divided by v and then flooring it. And then I'm going to take my r values, and then I'm going to be adding them to this little list in this case. So I'm going to be constantly recording those things. So unlike the extended Euclidean algorithm where I don't care about the r's after I'm done with them, in this case I do want to record these things as a very large list. So I'm going to be constantly shoving those into this list. And in this case I'm going to be shoving them in from the starting place. And then at the very end, I'm simply going to return that string or that list R back to the user. So if I look at it on this pair, 37 and 2, you can see that I take the 37, I divide it by 2, giving me a quotient of 18 and a remainder of 1. And then I take the 18 divided by 2, then the 9 divided by 2, then the 4 divided by 2, the 2 divided by 2, all the way until I get this little value of 1. You can see that I get my quotient of 0, which tells me, hey, I'm done at this point in time, and then I can return that little list back to the user. In this case, the list is 100101. And that's the one that we hopefully saw earlier that connects the 37 into a base 2 version, and then I can actually bring it back to the base 2, or I can bring it back to the base 10 representations as well. The one thing that I want to note in this case is that a lot of programs actually have some of this utility built into it. In this case, Sage is no different. If I were to compute 313 with this digits command, if I input the 2, what's going to happen in this case is that it's going to record this base 2 representation of this thing, but it's actually done flipped. So 313 is weird because it is a nice palindromic number base 2, so it looks the exact same forward and backwards. But if I look at this thing, let's say base 3 or base 5, they are properly going to be flipped around from what we're used to seeing them in this case. So if I take 313 and run our little algorithm that we saw up above and convert this thing base 3, we see that it's going to be of the form 102121. That is, this 1 right here is then going to correspond with the largest power of 3. So I have a 0 term, a 1, a 2, a 3, a 4, and a 5. So that becomes my A5 term. A lot of times people will actually flip that around, and that would then be the last term on the list that's returned. And that's exactly how Sage's digits command works, is that that little number here technically becomes the last term in this list. And the justification for that is that if you look at the number 37, sometimes we view this as 3 times 10 plus a 7, but you could also view this as 7 plus 3 times 10, which is 7 times 10 to the 0, plus in this case a 3 times a 10 to the 1. Likewise, if I looked at the number 313, this could also be viewed as 3 plus a 1 times a 10 plus a 3 times a 10 squared. So it all depends on if you want those exponents in increasing order or in decreasing order. I tend to like to write them in this decreasing order, so the idea is that I'm going to put the largest exponent first, which is why that AK becomes the first term in that list. But it's also very common to record that as the last term in the list as well. So just be aware of whatever utility you're working with as how they're actually going to represent those things. This little procedure that I did up above, because I was inserting these R's in the beginning of the list, it's going to be recording those things from largest exponent down to smallest exponent. The built-in command inside of Sage is going to have it flipped around. You can easily just use this reversed command to actually flip it, but just be aware of what those weights are technically representing, because it's really easy to have a nice little process constructed, but the wrong order of things. So you want to be very careful as to how you're going to be running through these lists, if you're going to be going from largest to smallest or smallest to largest. So just be aware of that as you begin to implement some of these.